Hello, I'm Boris Zimmermann. I work as a researcher at Realtech, and I will show you the equipment that we have here in biospectroscopy laboratory at Realtech. This is Bruker Vertex 70 Fourier transfer infrared spectrometer, and it has the central unit and two accessory units. One is Hyperion 3000 microscope, and the other one is HTS-XT high throughput unit for fast screening of samples. This is the central unit, the Vertex 70. It has the main compartment here, and we can use it for standard transmission measurements. Standard transmission measurements, they are the simplest form of infrared measurement, where we put the sample on the path of an infrared beam. The light goes from here, so we have a broadband source of infrared radiation. It passes through our sample here. Part of the light will be absorbed, and then the rest of the light goes here, and it's recorded on one of the two detectors. One detector is very sensitive, but we need to cool it down with liquid nitrogen, or we can use the other detector that works on room temperature. In order to do this, our sample needs to be transparent in infrared, like this foil. Instead of transmission measurement, we can also use reflectance method. In this case, light goes through this unit. It's called attenuated total reflectance unit. And light passes through the optical setting in the unit, and it's reflected on this crystal here. It goes back, it enters and goes to detector. On the crystal itself, we can put our sample and then measure it in reflectance, because light will penetrate through the crystal into our sample and measure partly the chemical composition of our sample that is in contact with the crystal. In reflectance measurement, we can measure samples that are not transparent, like this completely black foil. We do this by putting the sample on the crystal, and then we put a pressure on our sample in order to make a good contact between the sample and the crystal surface. We can also measure a liquid with ATR unit. We just put a droplet of our sample directly on the crystal. And in this case, we already have a very good contact between our sample and the crystal surface. Bruker instruments use Opus software for data acquisition, and we can also do post-processing of the spectra. This is a typical spectrum of biological sample, and here you can see at what infrared light frequencies your sample is absorbing or transmitting light. In this case, we have absorbance units here, which means that the signal intensity is corresponding to the amount of light that was absorbed by the sample. Molecules are absorbing light. The more light they absorb, the higher is the signal. And the signal can be shown either as transmitted light, or in this case as absorbed light. So the stronger the signal, the more light was absorbed. Next to the main unit, Vertex 70, we have HTS-XT high throughput unit for a fast measurement of large amount of samples. It's connected to the main unit because it uses infrared source of radiation that goes through the unit. It passes through our samples, and it goes to internal detector. Usually we prepare our samples as suspensions, and then we put small droplet in the well We wait until solvent evaporates and creates a nice film. When we have prepared all the samples, we put the plate in the instrument, and then the measurements will be done in quick succession between each sample. Next to the main unit, we have Hyperion 3000 infrared microscope. We use it to focus infrared light on very small part of our sample, and we can obtain individual infrared spectra of relatively small area, or we can map a bit larger area and get something that is called infrared chemical image. Similar as in normal optical microscopy, first we need to put our sample on a slide. Unfortunately, glass is not fully transparent in infrared part of the spectrum, so we need to use a bit different materials. In this case, we are using zinc selenide window, and on top we have put a dry, relatively thin film of our sample. We can use different type of objectives. In this case, we have 15 times magnification that we can use in transmission or reflectance measurement. And we can also use ATR objectives similar to the main unit that we have used in the Vertex 70 main compartment. Here you can see a typical chemical imaging of a sample. By selecting different type of chemical signal, we can create different type of chemical images by highlighting different type of chemistry in our sample. You have your optical image where you can see what you're measuring with infrared radiation. At each point, you get a full infrared spectrum with full range of frequencies. You can focus on a specific type of infrared frequencies. For example, these ones, they correspond to carbon-hydrogen stretching. And then you can map in what part of your image you have high absorbance of this type of radiation. This is a matrix MF, Fourier transform infrared spectrometer, again from Bruker. We use it for probe measurement of liquids. So the instrument has an infrared probe connected with fiber optic to the main unit. The tip of the probe contains a diamond crystal that can record spectra in a reflectance mode. It works in a similar way as the ATR unit that I have shown in a Vertex 70 instrument. In order to record the spectra, we just lower the probe into a solution or a bioreactor, and then we can monitor the process during a longer period of time. We can record spectra for several hours up to several days. The instrument uses Opus software for data acquisition, and during the process monitoring, we can get several hundred spectra recorded, and we can check which infrared signals are changing in time and how our chemical or biological process is progressing. Here we have Bruker multi-ram Fourier transform Raman spectrometer. The instrument itself, it has several compartments. Here we have a huge liquid nitrogen tank for cooling of the detector. We have a source of radiation, and that's a single frequency laser. It uses infrared radiation at 1064 nanometers, which makes this instrument a bit unusual for Raman instruments. Usually Raman instruments are using laser excitation in the visible part of the spectrum, but this one is using infrared radiation a bit higher than visible light. Similar as infrared spectrometers, Raman spectrometer has a central compartment where we can measure different types of samples. We can measure either solid samples or liquid samples, and unlike infrared spectrometers, we can put our samples in glass vials because glass is transparent for Raman radiation. The source of radiation that we use in Fourier transform Raman spectrometer is also infrared light, but unlike infrared spectrometer, it has only one frequency at 1064 nanometer, and this light is relatively close to the visible light, which means that it can pass through glass, and because of this, we can record Raman spectra of our samples by using glass holder or glass vials like here. Measurement is relatively simple. You just take your sample, you put it on a path of excitation laser, and you record the light that is scattered by your sample, but scattered with a bit different energy than the excitation laser itself. Similar as in infrared spectroscopy, with Raman spectroscopy we can also use fiber optic probes like this one. So it's connected with fibers to a main Raman unit, and we can measure remotely samples just by holding it next to a probe. The Raman effect will be expressed in a way that sample absorbs part of the energy from the excitation laser, and the reflected light or the scattered light that goes back to the detector has a bit lower energy. The absorbed light corresponds to vibrational energy states in the molecules. The more energy is absorbed, we have a higher intensity signal of Raman radiation. In this room, we have a robotic system for preparation of samples for high throughput measurement with infrared unit.